Now let's think about what do our slope and intercept represent? What do they mean? Let's start with our slope. We'll start with our 6.02. What a slope typically measures is for every unit increase in x, for every additional increase in x, y is expected or predicted to increase or decrease by that amount. So for this problem, for every inch that one person gained, for every 1 inch gain, one would expect or predict a person's weight to increase by 6.02 pounds. That's what our slope is saying. For every additional increase in x, the expected or predicted weight goes up by 6.02. Our intercept does something a little bit differently. What this says is when x is 0, what would y be? So if somebody was 0 inches tall, they are expected or they are predicted to weigh negative 251.74 pounds. That doesn't seem right. Right? If somebody is 0 inches tall, they weigh nothing. They should weigh 0 pounds. Unless we're dealing with black holes and dark matter and I don't know, all that jazz. Right? But typically, if somebody's 0 inches tall, they would weigh 0 pounds. That's what our intercept does. It essentially makes a prediction. When x is 0, what is y? What do we predict? What do we expect y to be? And this particular prediction is very poor. We would expect them to weigh 0 pounds, yet our regression model is telling us that we should expect negative 251.74 pounds. Oddly enough, even though our intercept doesn't really make sense, what we're doing with our intercept is what we should be doing with regression models compared to our slope. If I was to draw out using height to predict weight, and I was to draw out these 11 data points or so, something like that, and then we find the line that best fits your data, we shouldn't be thinking about our slope in terms of its interpretation. And the reason being is that where causation comes into play. Now, it probably makes some logical sense that the taller somebody is, the more they should weigh, right? Typically, the more mass somebody has, the more they weigh, right? So that's not a crazy jump. But in our interpretation of a slope, this has to do with the causation aspect, which is not typically what we want to do with regression. If we increase x, decrease x, what happens to y? That causation is not what we are using these regression models for. Our intercept interpretation, this is interpretation based on a prediction. What do we predict y to be when x is 0? This is something that we want to use these regression models for typically. Even though our prediction seems awful, the concept of our interpretation of an intercept is better than that of a slope. Because we're not saying, well, if you increase x or decrease x, what's the cause of y? We shouldn't do that. We can use these for predictions, but we may not want to use them for this causation aspect unless we know. But why does this prediction make no sense? Well, let's think about this in another way. Suppose Professor O popped out a baby, and the baby turned out to be 20 inches tall. How much would we expect him or her to weigh? Now, I think about this problem in reality, right? So imagine a woman is pregnant with a child, and I get, how you can ultrasound the baby, get a sense of measurements to figure out its height. But figuring out the weight of a baby seems to probably be a lot more difficult before it's born than its height, right? The ultrasound, you can get a sense of the height. I don't really know how you'd get a sense of the weight. So suppose you wanted to use this regression model to predict how much your baby was going to weigh when it comes out the womb. It turns out that a typical baby is 20 inches tall. Let's do this out. Our intercept was negative 251.74. And then we're going to add the quantity of our slope. And now we're going to take into account the height of our baby. I mean, that was the point of these regression models, to make predictions. So let's make a prediction. If we were to do this out, our predicted weight would be a whopping negative 131.34 pounds. Not a very healthy baby. Why? Why is our model so off? Well, if we go back to our model, we were using data from 11 adults. No babies were used to come up with this model. Therefore, the model we create is not going to do a good job of estimating babies since no babies were in our sample. Again, our goal of statistics is to use a sample to estimate something about a population. If our sample doesn't have babies, it's probably not going to do a good job at estimating babies. So we need to keep in mind the concept of statistics. Using a sample to estimate our population, it better be representative of what we're after. What we just did was extrapolate. Extrapolation is when you try to predict outside of the scope of your data set, right? No babies were in our model, thus we shouldn't be trying to predict babies. We didn't have anybody that was 20 inches tall in our model, thus we shouldn't be trying to predict people that are 20 inches tall. Interpolation is what we should be using these regression models for, and that's predicting inside of the scope of your data set, where your sample represents your population. So this model could be doing a good job of estimating adult height. Now, it was only 11 observations, but we could use it to predict adult height. We shouldn't be using it to predict elderly height, child height, baby height, or people that don't exist height. So it's important to keep in mind what you're using these predictions for and what you'll be able to learn from your regression models.